conspicuous to one species may not be conspicuous to another. And this variation in visual sensitivity stems from two main sources. One is that there's variation in the number of cone cells that animals have in their retinas. So here we have this beautiful male rainbow darter who ironically only has 2 cone cells in its retina, a blue cone cell shown by this blue curve here, and this red cone cell shown by this red curve here. We have wavelength on the x-axis and the relative probability of absorbing a photon of light on the y, and the dashed line simply refers to the sensitivities of the rods. As most of us know, humans are trichromatic and possess a blue and a green and a red cone cell. Birds and insects and many fishes are tetrachromatic, where they have 4 different cone cells, including a UV, a blue, a green, and a red. And not to be outdone, bluefin killifish, which I've been studying for a number of years, have 5 cone cells, including a UV, a violet, a blue, a green, and a red. And not only is there variation in the number of cone cells that animals have, but there's also variation in the spectral sensitivities. We can look up at this male rainbow darter and see that the red cone cell is particularly red shifted. We can look at the human and see that the blue cone cell is particularly blue shifted. And of course, both the bird and the killifish are sensitive in the ultraviolet. And so this has presented a number of problems for us over the years, and a number of people have published papers trying to develop methods that allow us to measure animal coloration that are free of our sort of human subjectivity. And this includes work that's been done by the late John Lithgow, also work that's been, papers published by John Endler, more recent work that's been done by Robiev and Osorio that provides basically the methods for which most of these visual detection models work that many of us rely upon. And also there's a recent paper that was published in the American Naturalist where they said that not only do we need to know something about the number and the spectral sensitivities of the cone cells, but we also need to know about the wiring of the retina to be able to measure animal coloration. Okay, so measuring animal coloration is really hard and really complex. So the impetus for this talk is actually this picture. So this is a scan, but I have this picture framed, and it's on the wall of my office. And I have a couple of different graduate students that study the evolution of color patterns and speciation in darters. And we would invariably be sitting in my office saying, well, sorry, I should say this is the male rainbow darter and this is the female here. And we'd say, well, the male has this red on its anal fin, and the orange throat darter doesn't, and the currant darter has this, and the strawberry darter has this. And this conversation would eventually devolve into this, well, how do we know that these are real? I mean, this is a painting. An ichthyologist went out, collected these fish, and painted it. How do we know that any of this actually represents what real color patterns are? And it would just, it turned into this crazy conversation about philosophical issues about how we go about measuring coloration. And so we wanted to ask the question, well, how bad is it? How bad is it relying on human vision to detect variation in coloration in nature? And I want to preface this by saying, we accept the fact that we're blind in the ultraviolet. We accept the fact that we can't see polarized light. We accept the fact that we can't see the far red. But in the visible spectrum, how bad is it? How well do our eyes do at detecting these color patterns? And so to address this question, we adopted a methodology that most visual ecologists would say is fundamentally flawed. In fact, I had a visual ecologist buddy who said, Becky, I told him what I wanted to do. He said, Becky, don't do this. You're wasting your time. These data will be trash. And what we wanted to do is we wanted to compare a methodology that's heavily human biased with a methodology that's free of human perceptual biases. And in my ideal world, we would have studied fish, but when you preserve fish and stick them in ethanol, they lose their coloration. So I went to the dark side and we did a study on birds. And what we did is we compared the actual reflected spectrum. For this woodpecker, we might do it from its back and from its head. And we compared this with the reflected spectrum out of a field guide. And so the red off its head, the black off its back, and we also compared this with data on RGB data from a photo from a bird that we from the birds that we took. And so there are 3 data sets. One is the actual reflected spectrum from the preserved bird, which should be free of human subjectivity. We took RGB values from a digital photograph of a preserved bird, which is somewhat of a human bias because the R and the G and the B are meant to correspond to the various visual properties of the human visual system. And then we did the unthinkable, and we took the reflected spectrum from a field guide of a bird, which is highly human biased. Okay, so there are lots of reasons why the field guides should get it wrong. So let's think about what has to happen. So here we have this ornithologist, Louis Agassiz Fuertes, I hope I'm pronouncing this correctly. He sees this woodpecker, and he wants to get it into Birds of New York. But of course, it's not a photo that's in Birds of New York. It's a painting. So it's a duplication of a painting that has to go into Birds of New York. So first of all, the ornithologist has to see the bird and has to process it through through the human visual system. Then it has to paint it with these various paints that have these spectral properties of the various paints. And then this picture gets decomposed into these 4 channels. And these channels should look familiar to anybody who has a color printer, in that there's a cyan, this yellow, magenta, and black. These 4 channels get overlaid to make this picture here, which is how we get colored prints into our various field guides. And so this should completely mess up the reflectance spectrum. Okay, so what we did is we measured the reflectance spectrum from birds in the museum, using your ocean optics, lamps and reflectance probes and all that. We used birds that were in the Illinois Natural History Survey, so these tended to be Midwestern birds, but we tried to get a bunch of birds that were bluish or red or yellow. We had females that were brown, and we did the black parts and the white parts. So we tried to do this as broadly as we could. Here's a scarlet tanager here. If they were sexually dimorphic, then we measured parts on both the males and the females. And the really critical thing is we had 73 different unique combinations of what we think of patch elements by species by sex. So 73 different parts on the bird from which we had the data for those 3 different data sets. So we have the reflectance spectrum. We also took a digital photo and we have the color checker in so that we could standardize across cameras and standardize across slight variations in the lighting that we used. And then we measured the reflected spectrum from the same patches from the field guides. And so we have these sort of matching data sets. So for this the scarlet tanager, we had data from its breast, from its wing, and from its back. And similarly, we have data from its breast, its wing, and its back here. We compared these reflectance spectrum from the actual birds and the field guide birds. And then we also performed a principal components analysis on these 3 data sets. Okay, so what I'm going to do first is I'm going to show you some of the data where we just compared the field guide reflectance spectra and the actual bird reflectance spectra. Oh, I skipped ahead, sorry. We had actual reflectance from the field guide and the RGB photos. The predictions, if human vision fails to detect the relevant variation in animal coloration, then the first prediction is that the reflected spectra from the actual birds will fail to match that from the field guides. And also, for the principal components analysis, if you have principal components analyses of the actual reflected spectrum, the field spectrum, and the RGB data, then these, if human vision is doing a poor job, then these should reveal drastically different variance structures in the way that the PCs load onto the various things and the proportion of variance accounted for each of them. Okay, so what I'm going to do now is I'm going to show you some examples. And in general, we have found very similar patterns for all of the red sort of red color elements. So this is a graph for the male scarlet tanager back. The blue line is for the field guide, the black line is for the real bird. The wavelength is on the x-axis, the percent reflectance is here on the y. These little dots down here indicate whether or not there's a statistically significant difference between the reflectance at that given wavelength. And so what we can see is that there's a lot of statistically significant differences here, but in general, these curves are doing a pretty good job. So, surprisingly, this field guide captures this UV hump here. It goes down, and then both of these curves sort of jet out around this 580 region. The field guide always sort of plateaued at a higher level than the real birds, and so these curves don't lay on top of each other. But in general, the shape of it is actually pretty good. Now we get a very different pattern when we look at the yellow elements. So here's the data for the female Canada warbler chest. And again, these results are very typical of what we see for many different yellow elements. So let's look at the real bird first. So here we see this sort of hump in the UV here. It goes down, and then it has this very smooth spectrum going up. It goes up in the 500-ish range and then plateaus out. In contrast, the field guide does a poor job at capturing this. It has these 2 humps. And the reason for these 2 humps is that the field guide is combining two different dyes. It's combining the yellow dye and the red dye. And this is how color printers work. Color printers work by, instead of having these really smooth things, they have these things called metamers, where they can combine various dyes and produce the same cone output as you would as if you just saw this sort of pure color. And again, this is very typical for what we saw for yellows. The blues were ridiculously bad. So here we have the data for the male blue grosbeak chest. And again, the blue lines for the field guide and the dark ones for the real bird. And the real bird shows a stereo, what you would expect, and that there is a decent level of reflectance here in the blue and the field guide does quite poorly, and all the blues did very, very poorly. And this is again due to the fact that it's using a combination of dyes to produce, to produce the visual sensation as if you saw the real bird. And what it's doing is it's combining the cyan, which is way too far redshifted, but then it actually adds some magenta in to produce these two humps on these two sides. Okay, so just visually comparing the spectra, the reflectance properties of the field guide do a poor job, and they rarely match that of the actual birds. And this is because the inks used in the printing have different absorption properties than the pigments that are actually used by the birds. If we could print these things with carotenoids, it would do a much better job. But we can't. And so the red elements match relatively well. The yellow and the blue they do fairly poor. And these results suggest that human vision does a poor job of capturing the relevant variation in animal color patterns. Okay, so that's the first prediction. Now, given that those reflectance spectra are so far mismatched, given that they're so different, we want to ask the question, does the principal components analysis of the actual bird data set and the field guide bird data set and the RGB data set, do they reveal similar variant structures? You would think, given how poorly those two data sets match, that it would do a poor job. And yet you find the exact opposite. So, all right, so for the principal components analysis, so we have these 73 different bird elements. And so for each of those curves, there's like 90-some data points. So there's 90-some data points for each of those birds. And the principal components analysis for the actual bird can account for over 98% of the variation with 3 PCs. Similar for the field guide, they can account for over 99% of the variation with the 3 PCs. And the RGB, of course, there's just 3 variables there, so they can get all of it with 3. But what's even more impressive is that if we look at the proportion of variation that's accounted for by PC1, PC2, and PC3, we see very similar patterns. So PC1 for the actual bird accounts for about 70% of the variation. For the field guide, it's about 78. PC2 is somewhere between 16 to 22% of the variation, and PC3 is about 5%. Similarly, if we go and look at the PC loadings, so the PC loadings onto the reflectance at each of those wavelengths, we again see very similar patterns. So here we have wavelength on the x-axis, and PC loadings here are on the y. The blue dots are for the actual birds, and I guess it shows up as red here, are the field guide birds. And we see a very similar loading, and this is matched by what we see for the RGB loadings. So for all these, there's a heavy loading on these red wavelengths and somewhat on the green, and very low loadings here on the blue, which is reflected here in the RGB loadings. Similarly for PC2, we see a very similar pattern, where we see moderate loading on the reds, heavy loading on the greens and the blues. And one of the things I find particularly interesting is where we see a big discrepancy between the actual birds and the field guide birds is here in this UV region. So if you were going to predict a priori where you think there would be a big discrepancy between the actual birds and the field guide birds, knowing that we're blind in the UV, you would expect that discrepancy to be in the UV, and lo and behold, there it is. But the rest of it, it's not perfect, it's not the exact same thing, but it's pretty close. And we see a similar thing for PC3, where PC3 loads heavily onto these middle wavelengths and negatively onto the red and to the blue shown here. The other thing we can do is we can look at the correlation. So for each of those 73 different color elements that we measured, we can look at its score in PC1 for the actual bird, the PC1 for the field guide, and the PC1 for the RGB, and look at how strongly they're correlated. And lo and behold, if you look at the correlations between the actual bird PC1 and the field guide PC1 and RGB PC1, we see very strong positive correlations with the correlation coefficient over 0.9. If we look at the correlations for PC2, these aren't quite as strong, but they're still very, very positive. And there is one outlier there, which I'm told is the mountain bluebird wing, and something is funky going on there. And similarly for PC3, we see a strong positive loading here between the actual bird PC3 score and the RGB PC3 score. Okay, so I want to come back to these tables again and just sort of emphasize the fact that, the reflectance spectra from the field guides was completely wonky. It didn't match the